Before we do our story problem, let's come back for a moment and talk about our intermediate value theorem. The intermediate value theorem is this. Now, I know this is a lot of mathies, so let's talk about what it means. Let's draw a picture. So it says, first off, f is a continuous function. So that means I can draw it without lifting up my pencil. Continuous. And it's on an interval from x equals a. So let's do one right here. Let's call this one x equals a. It's an x value. And x equals b with a is less than b. So that's what we have here. We have a is less than b. And they're both on the x-axis. Now it says we're going to look at f of a and f of b. And they have different signs. So let's say f of a is here. So the f of a is just the y value for the function at a. And f of b is here. The y value for the function at b. And we know from f of a to f of b, this is continuous. We don't know what it looks like, but we know it's continuous. So maybe it looks like that. Who knows? Maybe. But it is still one continuous line from this point to this point. Notice I didn't lift up my pencil once from point to point. So here we have a is less than b. F of a and f of b have different signs. And it says, then we know that this graph f has at least one zero, aka one x-intercept between a and b. And we can see this is true. We came right here, there's our x-intercept. So it's essentially saying that if it's continuous and the y value goes from negative to positive, it's going to have an x-intercept somewhere between those numbers. That's what this intermediate value theorem says, which seems kind of duh when you really have it set out for you. If I go from negative to positive or from positive to negative, of course I'm going to have an x-intercept in there somewhere because I went from negative to positive, so it's going to be 0 somewhere. That's what the intermediate value theorem is talking about. So if you make, say, a number line, and you know this number line goes, if you plug in x equals 2 into the equation, and your answer is positive, and then you plug in x equals 4 into your equation, and the answer is negative. That means somewhere between 2 and 4, I'm going to have an x-intercept. That's the intermediate value theorem. So let's apply it. We want to use the intermediate value theorem to show that there is a positive number whose square is 2. So I want some positive number, I don't know what it is, so I'm just going to call it x, that when I square it, the answer is 2. And I just basically want to use the intermediate value theorem to prove that this number exists. I don't need to know what the number is, I just need to prove it exists. So here's what I'm going to look at. If I square 1, I get an answer of 1. If I square 2, I get an answer of 4. So if I have an answer from 1 to 4, doesn't the intermediate value theorem say that I'm going to hit 2 somewhere between those numbers? However, that only works as long as it's continuous. So this function we're using is x squared. So let's look at what this looks like. I have 1 squared is 1, and then I have 2 squared is 4. Can I draw the x squared graph from this point to this point with a smooth continuous line that doesn't move? Well, yeah, I can. This is a continuous function. It doesn't have any breaks in it. So because x squared is continuous, the intermediate value theorem says that if this one is at 1 and this one is at 4, then I am going to hit 2 somewhere between here. So yes, by the intermediate value theorem, I've proven that I'm going to hit 2 somewhere between these numbers because it's continuous from 1 to 4. So that is what the intermediate value theorem says. That's one example of how to apply it. The last video we have is our story problem, and we'll do that, and we'll be all done.